this afternoon session, at least in local time. So it's a pleasure to welcome Inbar Klang, who will talk about equivariant factorization homology and tools for studying it.
Thank
Please,
you.
go ahead.
Thank you. And yeah, it's great to be here, and thank you all for coming, even though we can't actually all just go to Barcelona and see each other in person. Yeah. But anyway, so yeah, I'll talk about equivariant factorization homology and some tools for studying it. And this is joint work with Asaf Boliv and Foling Zhou, and this also has an appendix by Jeremy Han and Dylan Wilson. So just a note, ask questions whenever you have questions. You can, if you don't want to raise your hand and unmute yourself, you can also ask in the chat. I'll be watching the chat as well. Okay, so I'll talk about what factorization homology is and what equivariant factorization homology is as well. But first, I'll just start with a bit of an overview of what the project is about. So here's what this is about. So we're studying G-equivariant factorization homology. So here, G is a finite group. So we usually denote factorization homology with this integral thing. So here, M is some manifold with G action, and A is some sort of equivariant algebra. And it's usually, for us, it's going to be a G space or a G spectrum. Okay. So here's one example of some previously studied invariant that can be described as an equivariant factorization homology. So real topological Hochschild homology of a ring spectrum with anti-involution is factorization homology of that ring spectrum over the manifold that I'll call S sigma. So this S sigma, this is the circle with reflection, C2 action. So C2, that's the cyclic group of order 2. So this THR, that's a real topological Hochschild homology. So this is a C2 equivariant version of topological Hochschild homology. And it approximates real K theory. Okay, so this is the kind of object that we're studying. And so before I go into more detail about what factorization homology is and what equivariant factorization homology is, I'll give some kind of flavor of the results that we'll talk about. So, so let's say overview of results. All right. So here's a theorem that we call equivariant non-abelian Poincare duality. So this has sort of been obtained both by Foling in her thesis and by us in our project, sort of different versions. So so this is if X is a pointed G space, and we're going to want to impose some connectivity assumptions on it. Then the factorization homology of the manifold M with coefficients in the V-fold loop space of X is equivalent to a space of pointed maps from the one-point compactification of M to X. So here, this upper plus is one-point compactification. Here, V is a G representation, finite dimensional G representation. And by loops V of X, I mean the space of pointed maps from the V sphere into X. So I'll talk more about this theorem and why we call it equivariant non-abelian Poincare duality. But maybe one thing to say about it at first is that it relates something that's typically thought about as a configuration space type thing to a mapping space. So this kind of has a long history going back in algebraic topology of modeling mapping spaces with configuration spaces and vice versa. So that's kind of one of the things that this theorem is saying. So there's a question in the chat. Does M also have a G action? Yes, yes. So, oh, right. So let me say what M is. So here, M, a G manifold, also with assumptions. And I'll say what these assumptions are more precisely later. There's also a question, does map mean G equivariant maps? So no. So here, this mapping space, so maybe I'll write this here. This is all pointed maps. And it's a G space with a sort of action coming from, you can call it conjugation or whatever. So source and target. Yeah, so this is going to be an equivalence as G spaces. Exactly. Yeah, thanks. So let's see. Oh, so there's also a question. One of the sides depends on V and the other one doesn't. So maybe I'll say that this, the precise assumption on M is we'll want it to be V-framed. So its tangent bundle is actually a trivial bundle, and the fiber is the representation V. So right. So for this theorem, it's also M is kind of modeled on V, and so this is why we get this kind of equivalence. Okay. So that's this theorem. Another one, which I'll state kind of very vaguely for now, is that equivariant factorization homology behaves nicely. Let's see. with respect to taking Tom spectra. Okay. So this is in some sense the factorization homology functor commutes with the Tom spectrum functor. I'll say more about that. But this allows us to compute certain equivariant factorization homology for some Tom spectra. So for example, if we want to compute real topological Hochschild homology, we can do that for certain Tom spectra that are coming from spaces that look like this. So for example, we can recover the computation of real topological Hochschild homology of HF2, which is due to Duto, Moy, Korea, Henry. We can compute THR of the real cobordism spectrum MUR. And also in the appendix, Jeremy Hahn and Dylan Wilson leverage this to compute the real topological Hochschild homology of HZ. So I'm gonna refer back to these acronyms here so that I don't write people's names a bunch of times. But yeah, so these are the kinds of corollaries that we can get computationally from these two theorems. All right. So next I'll switch over to talking about factorization homology, just the ordinary non-equivariant kind to set things up for equivariant factorization homology. But I'll pause for a few seconds just in case there's other questions about these. All right. So let's talk about factorization homology. And this is the non-equivariant kind. Okay, so this takes as input an N manifold M, and in some cases you will want it to be parallelizable, but I'm not always going to explicitly state all the assumptions in this kind of, I guess, more intuitive overview. And an EN algebra A. And this EN algebra A, you can take this to be a space, a spectrum, or a chain complex, or other things. And then the output is this integral looking thing, factorization homology of M with coefficients in A. And this is going to be a space or a spectrum or a chain complex, respectively, depending on what A was. So wherever you take your algebra to be, that's the same place that this factorization homology is going to live. Okay, so what are some examples of things that we can plug into here? Some EN algebras. So if you take loops N of some space X, the space of pointed maps from the N sphere into X, that's an EN algebra in spaces. And maybe also it's worth saying that every topological abelian group so those are kind of the examples in the category of spaces. In the category of spectra, like, well, ring spectra are E1 algebras, commutative ring spectra are En ring spectra for every n. So these are the kinds of things we'd want to plug into this. Okay, so here are some properties of factorization homology. So one thing about factorization homology is, well, it has been axiomatized as a homology theory for manifolds. And this is due to Ayala and Francis. So what kinds of things come into this axiomatization? Well, there is a sort of dimension axiom that says if you evaluate on the manifold Rn, you just get your algebra back. So that's like the value of the homology theory on the point, or our most basic object in n-dimensional manifolds. There's some functoriality there as well with respect to the manifold and the algebra. And there's an excision axiom. So this is a way to characterize factorization homology as a kind of homology theory. Okay. It also recovers some invariants that that weren't a priori defined as factorization homology. So if you take the manifold to be the circle, then factorization homology of the circle with coefficients in A, this is equivalent to Hochschild homology or topological Hochschild homology of A, depending on which category you take A to be in. But anyway, this recovers Hochschild type invariance. So if you take factorization homology for higher spheres, this is higher topological Hochschild homology. Okay, this is a choice for notation. This is where I wanted to put the brackets. Sorry. Okay. Another property of factorization homology is that it gives a fully extended topological field theory. So if you want to, if you want to define this fully extended field theory on a manifold N, you take the factorization homology of N with coefficients in A. So this leads to sort of a class of examples of fully extended topological field theories. And maybe I'll also sort of briefly mention that in geometric representation theory, quantum character varieties of surfaces are also approached via factorization homology. So this is due to Bensby, Brochet, and Jordan. Okay. So those are some properties of factorization homology. And I am not going to give a precise definition of factorization homology, but I do want to give some intuition and a picture for how I like to think of it. So this is going to sort of reveal the perspective of thinking of factorization homology as a configuration space type of thing. So so maybe we'll go to the next page to do that. So here's intuition for factorization homology. And the way I like to think of it is that the factorization homology of M with coefficients in A is configurations of points in M with labels in A. So you can think if this is your manifold M, then you've got a bunch of points in it. And they are labeled by elements of the algebra A. And when points collide, you use the EN algebra structure to multiply their labels. So for example, if these 2 points, A4 and A5, collide here, you'll label this point by A4, A5. Right, so there's sort of many ways to make this kind of intuition precise. So I guess if you want to make this precise, there's the axiomatic approach. So the kind of approach that I mentioned above by Ayala Francis. And there's a more sort of explicit approach, which actually constructs this thing in a model of configurations of disks in a manifold, and then what happens when you have an inclusion of disks into a bigger disk. So so as a two-sided monadic bar construction, you can also approach it that way. So there's many names that of people who have thought about it this way. Maybe I'll say Siegel, Andrade, Salvatore, Alexander Coopers, and Jeremy Miller, and probably others. So this is kind of the picture for factorization homology, this labeled configuration space where you encode multiplications by collisions in the manifold. Okay, so here's the non-abelian Poincare duality theorem for factorization homology. So yeah, so this has sort of been formulated in many ways, different times. So I'll just write down some versions of this. So this says that if M is a parallelizable N manifold, and A is an EN algebra in spaces such that its pi 0 is a group, so a group like EN algebra, then the factorization homology of M with coefficients in A is equivalent to the space of pointed maps from the one-point compactification of M to the n-fold bar construction on A. So Bn, this is the n-fold bar construction. Okay, so I'll say something about why this is even named Poincare duality. So why is this Poincare duality? So this has to do with what happens in the case where you specialize to A being a discrete abelian group. Then the factorization homology by Tom is going to be sort of a space model for the homology of M with coefficients in A. So the left-hand side gives you homology. And for the right-hand side, well, BNA, that's going to be the Eilenberg-MacLane space, KAN. So the homotopy groups of this space of pointed maps are going to be a shift of the reduced cohomology groups of the one-point compactification of them with coefficients in A. So in particular, say for a parallelizable closed manifold, you get the statement of Poincare duality, that homology and cohomology are isomorphic. So then this is called non-abelian Poincare duality because now we're not just taking coefficients in discrete abelian groups, but we're allowed to take coefficients in a more general class of algebras. So this is happening in EN algebras. Okay. So next I want to move on to introducing equivariant factorization homology, but I'll just pause here in case there's any questions. All right. There we go. So equivariant factorization homology. So here are some names of people who've worked on this. So Asaf developed this in his thesis. Tim Weilink, and also Foling in her thesis. And there's some others probably that I'm less familiar with. So this has input a G manifold M, so manifold with a G action, and in parentheses, maybe we'll want to say that it's a V-framed G manifold and an EV algebra A. So this is going to be a G space or a G spectrum. Right, so we'll restrict to V-framed manifolds for the time being, and I'll say what that means soon. And the output for this is the factorization homology of M with coefficients in A, which is a G space or a G spectrum, depending on what kind of thing A was. Okay, so I think EV algebras might be a bit less familiar than EN algebras. So maybe I'll just give some examples of things that are EV algebras. Okay, so for example, any G commutative algebra is an EV algebra for every G representation, V. So here V is a G representation, and the dimension of V is the same as the dimension of M. Right, so we can plug any G commutative algebra, either space or spectrum, into equivariant factorization homology. Okay, what does EV algebra mean if we take V to just be the trivial n-dimensional representation? Well, in this case, this is an EV algebra is an EN algebra with equivariant, let's say G equivariant structure maps. So an EN algebra in G spaces or G spectra. Okay, here's a more specific example of a representation. So if G is the cyclic group of order 2, and V is the sign representation, sigma, then an E sigma algebra is essentially a ring with an anti-involution. And so anti-involution, I mean, anti-involution of xy, anti-involution of x times anti-involution of y, or sorry, other way. So there's a question, is G spectra genuine or naive? So we'll be working in genuine G spectra in this talk. Okay, so another example of EV algebras that we'll be interested in are just the loop spaces, loops V of x. This is an EV algebra in G spaces. All right. So those are some things that we can use as coefficients for equivariant factorization homology. And we'll be doing that later when we talk about computations. So a lot of them are going to come from G commutative algebras, and a lot of the methods are going to be based on the fact that we're going to have a non-abelian Poincare duality theorem that tells us what happens for these loops V of x type of algebras. All right, so here's some intuition for equivariant factorization homology. And it's going to be similar to the intuition for ordinary factorization homology, as in we're also going to think of it as some kind of labeled configuration space. But now we have to think of the G action sort of intertwining everything. So, so maybe I'll say it's a labeled configuration space. So labeled configurations of orbits in M. And these orbits are labeled by A. And you can think of this as intertwining the action on M and the action on A. So here's maybe a picture for the G fixed points of this equivariant factorization homology. So whenever we discuss equivariant factorization homology, this is also an equivariant object, either a G space or a G spectrum. So we can ask about its fixed points. In the case of spaces, it is just fixed points. In the case of spectra, this will be the description of the geometric fixed points. So here's a picture for this. So maybe this is our manifold M, and we have some points labeled by elements of A. And so one thing that happens in this kind of configuration, for example, is that if you act by G on a point and move it to a different point, then you also act on the label by the same element G. So here are some rules for how these labeled configurations work. So for example, for a point, let's call it x1 in M, if some G times x1 is x1, then the same for the label. So G of its label is also the same. Okay. Another thing is the thing that's happening in the picture. So if, say, x4 is equal to G of x2 in M, then the same is true for the labels. So A4 is the same as G of A2. And maybe something that's a bit more subtle that's happening here is, for example, what happens when an orbit collides into a fixed point. So first, maybe I'll say if fixed points collide, just multiply their labels as you normally would in ordinary factorization homology. And lastly, if an orbit consisting of all of the actions on X collides into a fixed point, then you label that fixed point by the norm. So you label it by the product of over all the G's and G's of G times the label of X. Yeah, so this is kind of something that's coming from the genuine equivariant structure here. We don't only have sort of multiplications after forgetting the equivariant structure, but we also have these equivariant multiplications coming from norms. Okay. So here are some properties. So this is a picture, and maybe I'll say something about ways to make this precise. So you can make this precise axiomatically in a way that sort of follows the Ayala-Francis approach as a homology theory for manifolds. So this is the approach that Asaf takes. And Tim Whaling's work is also based on this kind of thing, but with the axioms being a little bit different. Or you can also describe it as a monadic two-sided bar construction. And this is the approach that Whaling takes. So again, there's ways to make this precise. Okay, so here are some properties of equivariant factorization homology. Okay, so you can think of this as a homology theory for G manifolds. So for example, if you take the equivariant factorization homology and evaluate it on a G representation, you just get the algebra back. There's functoriality, and there's excision. And because the equivariant world is more complicated than the non-equivariant world, there's sort of more than one way to formulate these axioms. So one of those ways is the one that we're talking about. So the one due to Asaf, and it's called genuine equivariant factorization homology. So that's when you require that all norms appear and behave the way that they should. Okay, so another property of this is that it recovers certain G equivariant versions of topological Hochschild homology. So Asaf showed that if you take factorization homology with manifold being the circle with reflection action, then you get the real topological Hochschild homology of A. And also, if you want to recover relative CN relative topological Hochschild homology, you can take the geometric fixed points of equivariant factorization homology, where the manifold is the circle with Cn acting on it by rotation. Right, so just like in the non-equivariant case, a lot of the Hochschild type invariants show up as factorization homology. All right. Yeah, so this is kind of some introduction to equivariant factorization homology. So maybe next I'll say, more about the non-abelian Poincare duality theorem that applies in this case. So here's the theorem. And there's sort of two different versions of it. So let M be a V-framed G-manifold and X pointed G-space. And we'll have some connectivity assumptions on this space X. Then if you take factorization homology of M with coefficients in loops V of X, then you get the space of compactly supported maps from M into X. And this is as G spaces. So this is what we call equivariant non-abelian Poincare duality. All right, so maybe there's a couple of things to explain about this theorem. So one of them is what V-framed means and what kinds of examples fall under that umbrella. And the other one is, why is this a Poincare duality type of theorem? So here's what V-framed manifolds are. So this is a particular equivariant version of being parallelizable. So this means that the tangent bundle of M is isomorphic to M cross V as G vector bundles. On M. So here are some examples of V-framed G manifolds. So the most fundamental one is just M being the representation of V. That is V-framed. Another one is if, so S sigma, so this is the circle with reflection. This is sigma framed. If you let Cn act on S1 by rotation, this is R framed. So by R, I just mean the trivial representation. And if we denote by SV, the sphere, which is the one-point compactification of the representation V, then SV cross R is V cross R framed. So this is analogous to the fact that spheres are stably parallelizable. So most spheres are not parallelizable, but once we cross them with the real numbers, then that's parallelizable. So the same kind of phenomenon happens equivariantly for V spheres. All right. So why do we call this theorem Poincare duality? So it's the same kind of idea where if we take homotopy groups, we recover some statement of Poincare duality. So let's take our loops V of X to be, say, the infinite loop space of the Eilenberg-MacLane spectrum HZ. We can take other Mackey functors as well, but let's just do HZ for now. So taking ROG graded homotopy groups of the equivariant non-abelian Poincare duality theorem gives an isomorphism between the equivariant homology groups of M with coefficients in Z and the cohomology of, well, the one-point compactification of M with coefficients in Z. So again, this is some statement of equivariant Poincare duality for V-framed G manifolds. And so then this one is non-abelian because instead of just taking these G commutative things, we can take any loops V of X as well. All right. So next, I want to talk a little bit about this theorem on Tom Spectra. So what's going on there and what corollaries we obtain from that. But before that, I'll pause in case there's questions about this stuff. Okay. So, right. So what's going on with Tom Spectra here? All right. So non-equivariantly maps from a space X to be O, for example. They classify vector bundles over X. And so then once you have a vector bundle, you can take its Tom spectrum. And I'll denote that X to the F. So for example, if F is null homotopic, then this Tom spectrum is just equivalent to the suspension spectrum of X. All right. So this is also something that works for equivariant maps. So equivariant maps F from a G space X to the equivariant BO classify G equivariant vector bundles. Over X. And so then you can take their equivariant Tom spectrum, which is now a G spectrum. So for example, if your map F is equivariantly null homotopic, you again just get the suspension spectrum of X. But there's a lot of other interesting things if F is not null homotopic. So here's the theorem about the interaction of equivariant homology so with Tom spectra. So equivariant factorization homology. I'll put it in quotes, commutes with the Tom spectrum functor. So here are a couple of things that this means. So for example, if you have a V-fold loop map from the V-fold loop space of X to BOG, then its Tom spectrum we'll denote this with this exponential notation, loops VF, loops VX to loops VF, is an EV algebra. So maybe I'll say this is also from our paper. Okay, so once you know that this Tom spectrum is an EV algebra, you can evaluate factorization homology on it. So the theorem is that the factorization homology with coefficients in this Tom spectrum is also a Tom spectrum. So this is going to be the Tom spectrum of the following map. So we start with this space, factorization homology of M with coefficients in loops V of X. And recall that by our non-equivariant Poincare duality theorem, this is equivalent to a mapping space. All right, we can use functoriality to map this to the factorization homology with coefficients in BO. And then we can sort of embed M in some large dimensional representation. And this is then going to be equivalent to BO itself. So there's a question in the chat, when is the equivariant factorization homology equivalent to the non-equivariant factorization homology? So if you forget the G action, it is equivalent to the non-equivariant factorization homology. So maybe a remark. Non-equivariantly, okay, I don't know how to say this, but so equivariant factorization homology forgets to non-equivariant factorization homology. All right, so so a lot of this is kind of an enhancement of things that happen non-equivariantly. Yeah, so right, so here this factorization homology with coefficients in this spectrum is also a Tom spectrum of some map. So it's going to be a map from this mapping space into BO, which is given by functoriality, and then embedding M into some large dimensional G representation. All right. So this is the theorem about Tom spectra. So there's a question in the chat. How do you see that? Is the equivariant co-limit diagram co-final to the non-equivariant? So I mean, so I don't know if that's exactly the language that I'm familiar describing it in, but so let's see. So let's see what do I say about this? Well, so the technique that we use here, well, this is happening in sort of G-parameterized higher categories, and it's all coming from the fact that the equivariant Tom spectrum functor is a co-limit, and that it's G-symmetric monoidal. So so maybe I'll write that down. That's where this is coming from. So so maybe it comes from the Tom spectrum functor is a co-limit, and it's G-symmetric monoidal, sort of in the higher categorical sense. And so therefore it respects factorization homology. Okay, so so maybe I'll just close with saying what kinds of calculations come from this. All right, so here are some corollaries. So one of them is that the real topological Hochschild homology of HF2 is HF2 smashed with the suspension spectrum of loops of S rho plus 1. So here rho is the regular representation of C2. And this recovers the description in the Tomoe Factorization array, which says that this is polynomial over HF2 with generator in degree rho. Okay. We can also find the real topological Hochschild homology of MUR, and this is going to be MUR smashed with the suspension spectrum of B sigma of BUR. And then there's also the computation of THR of HC. So this is HC, and then also wedged with some copies of age of Z mod K. So this is in the appendix by Jeremy Hahn and Dylan Wilson. And there's also some higher factorization homology things that we can do from there. So we can also find the factorization homology of HF2 on some higher dimensional spheres. And also the same is true for MUR. We can actually find the factorization homology of MUR on any kind of representation sphere, because this is a Tom spectrum of GE infinity map. All right, so I'll just say there are some interesting questions that stem from here that might be good to think about later on. But one of them is sort of, we have this non-abelian Poincare duality theorem. It's for V-framed manifolds. What happens for manifolds that are not V-framed? So in the non-equivariant case, there is a non-abelian Poincare duality theorem for manifolds which are not parallelizable. And it's given by some section space instead of a mapping space. So one good question would be to sort of find out what happens in the equivariant case. Do we also get some equivariant section space? Another thing is sort of finding some properties of these higher dimensional spheres for factorization homology. So what does higher THH but equivariant give us? So yeah, so thank you, and I think I'll stop here.
Okay, thanks a lot, Inbar. We can clap our hands the way we want. I'm online, so I do it in real life. And then I want to ask if there are questions or comments. Let me look at the chat. But I think I wonder how you can follow the chat while you give a talk, but it was, I think you got them all.
Can I ask a question?
Sure.
Yeah, go ahead.
Thanks for the nice talk. So I was wondering, so there are these equivariant versions of THH as well by 5-6 others like Blumberg, Gerhardt, Hill, and some others. If you have seeing those. I mean, are you also recovering that? kind of thing?
Yeah. So let's see. So maybe you mean these CN relative THH?
Oh yeah, okay, I see. Yeah, something like this. Yeah, exactly. Yeah, yeah.
Yeah. So right. So in this case, it's not exactly just a factorization homology, but it is the CN geometric fixed points of the factorization homology.
Oh, I see.
So right. So like this thing is kind of going to be equivalent to THH, but this S1 action is kind of
See.
intertwining the S1 action. Yeah. So anyway.
You're recovering those residual sort of.
Mhm, mhm.
I see. I see.
Yeah, exactly.
Okay, great, thanks. So basically, you can also use then these things for computing those kind of THHs as well, potentially.
Yeah, for sure. Yeah. So we use this theorem on the factorization homology commuting with a Tom spectrum functor. So this is joint work that I have with Tina Gerhardt and Catherine Hess and Catherine Adamic and Hannah Kong, where we use that theorem about the Tom spectrum functor to compute the THH-C2 of HF2 and H delocalized that 2.
I see. Okay, so that's a different. I mean, yeah. So that's sort of a different type of C2 THH than the.
Yeah.
Yeah. Okay. Cool.
Yeah, for sure.
Thanks.
All right. So there's also a question in the chat about this this description of the fixed points here, and it says, doesn't this look just like a description of the action? So, right. So I guess, I mean, it would be kind of hard to like just draw a picture for the equivariant factorization homology itself, because it would really be just labeled configuration spaces, right? Like you take your manifold and you label it by elements of the algebra. And so great, that's just factorization homology, excellent. But then the sort of interesting thing comes in when we say a bit more about that action. So describing the fixed points is a way of saying more about that action. And it's saying that in the fixed points, if we have points that are in the same orbit, then their labels must also be in the same orbit, stuff like that. If a point is fixed by the action, its label must also be fixed by the action. So those are things in that space of configurations that are fixed by the action of G on that space of configurations.
But isn't the action like diagonal action both on points and on the label?
Yeah, I guess you could think about it like that. Yeah. I mean, so we like to think of them as, or at least the fixed points are labeled configurations of orbits. But I think that would be, yeah, like it's incorporating both the action on the manifold and the action on the algebra in that sense.
Okay.
Are there any further questions or comments?
Parallel to TQFT case, does G-covariant factorization homology give rise to fully extended G-covariant TQFT?
Ooh, that's a good question. So I don't know about that because I guess, yeah. So there's kinds of different things that people mean when they say G-equivariant TQFTs. And sometimes I think, sometimes it means like TQFTs, but where the manifolds have tangential structure or stuff like that. So I haven't really yet seen a notion that's exactly like the thing that we're getting from equivariant factorization homology. But that's also another thing that would be interesting to think about. Yeah.
Thanks.
Okay, then maybe it's time to thank the speaker again so we can move on to the next. So thanks again, Inbar.
Thank you.